Welcome to our video about the biomechanics of a jump shot. We will begin by giving you a quick history of basketball and the jump shot. Basketball was invented in 1891 by a college coach named James Naismith as a way to keep his athletes conditioned in the winter months. The jump shot was invented by Kenny Sailors, who first introduced it to the world in 1943. He invented it as a way to shoot over his way taller brother. Shooting one-handed was amazing at the time because everyone shot with two hands. With the jump shot, he carried his team, the Wyoming Cowboys, to a 31-2 record and an NCAA title in 1943. He was also named the most outstanding player at the tournament. Without Kenny Sailors, the jump shot as we know today would not exist.
In each lever, there are three components that make it a lever: the fulcrum, the resistance, and the effort. The fulcrum is the pivot point that stays constant, the resistance is the force that is applied to the lever, and the effort is usually exerted either by muscles acting on joints or by heavy external objects acting on the human body.
Elbow flexion is a third-class lever because the fulcrum is found on the elbow. The effort is where the bicep attaches to radius and the resistance is on the hand. This means the resistance arm is longer than the effort arm, making it a third-class lever. Similarly, elbow extension is a third-class lever because the fulcrum is found on the elbow. The effort is on the olecranon process where it is attached to the bicep and the resistance is on the hand. In both wrist flexion and extension, the wrist is a class 1 lever. This is because the fulcrum is in the wrist. The hand is the resistance, and the flexors and extensors are on the forearm. This puts the fulcrum right in the middle of the resistance and the effort, making it a class 1 lever.
Throughout the jump shot, we can apply Newton's three laws to each phase. First, we'll be covering Newton's first law, which states that an object will remain at rest or continue to move with constant velocity as long as the net force equals 0. This is evident in phase 1 and 5. This law discusses the theory of inertia. All objects with the mass have inertia. The larger the mass, the more difficult it becomes to change the object's state of motion. This theory is most prevalent in the movement of the ball as well as the player jumping. Newton's first law applies to the ball. The ball rests on the player's hands in phase 1 because the normal force applied by the hands equals the force of gravity. Once the player has shot the ball, it will continue to move along a horizontal axis until the effect of gravity pulls it back down. In phase 1 and phase 5, the net force for the player equals 0 as they are not in motion. However, right when we approach phase 5, the net force for the player and the ball does not equal 0. As the player wants to jump off the ground, they must change their inertia from a horizontal movement to a vertical motion. This law also comes into effect once the player has left the ground for the jump. They will initially move upwards and only begin to descend when acted on by the force of gravity. In the next phase of the movement, Newton's second law will apply to change the state of motion for both the player and the ball. Newton's second law states that the acceleration of an object is proportional to the net force acting on it and inversely proportional to the mass of the object. For instance, you can see this in phase 3 and 4. In order to change an object's state of motion, a force needs to be applied. This theory can be applied to the jump shot as the player enacts a force on the ball to accelerate it out of its hands, causing the ball to suddenly gain momentum towards the goal. The ball moves forward and the player remains in the same position due to the mass indifference between the ball and the shooter. And lastly, we have Newton's third law, which states that for every action, there is an equal and opposite reaction. This is seen in phase 4. This phase occurs in the jump shot as the player applies a force onto the ground, and the ground will push back with the same force, causing the player to accelerate vertically off the ground. When the player throws the ball, a force is applied while the ball applies an equal and opposite force against them. Phase 1. Preliminary movement. In phase 1, the feet are shoulder-width apart with the favored foot slightly in front of the non-favored foot. The weight is equally placed on both balls of the feet to prepare for the next phase and will help result in a straight throw. The knees are slightly bent to lower the center of mass. The elbows are flexed underneath the ball. The shooting hand is behind the ball, and the supporting hand is on the side of the ball to guide it into a straight shot. The eyes and toes are toward the target. This alignment will aid in the direction of the jump shot, optimizing the accuracy. The principle that applies is Principle 1, which states that the lower the center of mass, the closer the center of mass to the base support, the larger the base support, and the greater the mass, the more stability you have. A low center of mass and the closer the center of mass to the base support is seen when the knees are slightly flexed. A large base support is seen when the legs are shoulder-width apart. The center of mass is important because the player must be as balanced as possible when undertaking the jump shot. This results in a stable preliminary movement. The feet are shifting weight as the heels start to lift from the ground. The hands are still flexed. The wrists are flexed back. The hands then draw the ball above the head. The principle that applies is Principle 2, which states that the production of maximum force requires the use of all possible joint movements that contribute to the task's objective. The knee, hip, trunk, shoulder, elbow, and wrist joints are used. Another principle that applies to Phase 2 is Principle 3. It states that the production of maximum velocity requires the use of joints in order from largest to smallest. The use of these joints add one after the other from Phases 1 until Phase 5. Next we have Phase 3, force-producing movement. In Phase 3, the feet are plantar flexed, the rotated torso is uncoiled, and the elbows are fully extended. The principle that applies is Principle 4. It states that the larger the applied impulse, the larger the increase in velocity, therefore the greater the change in momentum. The impulse-momentum relationship states that the impulse equals momentum. To transfer the player's horizontal or running momentum into a vertical one, the player will be required to apply a big force over a long time, meaning that less time will be spent on the ground and consequently more time is spent in the air, which leads into Phase 4. When this is performed, the force, F, is incorporated with T, time. Impulse is created, and therefore the greater the impulse, the greater the change in momentum. Next we have Phase 4, critical instant. In Phase 4, it is when the ball leaves the hand of the athlete leaves the floor, and the wrists are flexed. The principles that can be applied are 5 and 6. Principle 5 states that movement usually occurs in the opposite direction of the applied force. As the ground stays immobile, the feet make a downward applied force, which results in the ground pushing back on the player. Thus, the player can jump in the opposite direction to its downward force. The player's applied force on the ball causes the ball to apply a counterforce. Although the ball acts back on the player, it has minimal influence on the athlete's direction due to having a greater mass than the ball. Therefore, the player will not move backwards. Additionally, Principle 6 states that the angular motion is produced by the application of a force acting at some distance from an axis, that is, by torque. This is seen during ball rotation or backspin. When taking a jump shot, a backspin is put on the basketball. The backspin creates a high pressure below the ball and a low pressure above the ball, which helps lift it into the air. Wind resistance occurs against the direction of the ball. Turbulence is created behind the ball due to the chaotic change in air pressure and flow velocity. The effects of air resistance over the ball is so small because of the small velocities, so the spin of a shot in the air is not useful. What spin is useful for is for a better chance of the ball hitting the rim. The backspin, after contact with the back rim or board, will result in a change in velocity opposite to the spin direction, changing an equal angle rebound into a velocity more towards the net. Another important aspect of spin is energy transfer. With the spin of a shot, some of the energy is transferred into the basket. This transfer of energy is from friction. When the spinning ball hits the rim, more energy is transferred. Through this use of backspin, the ball will bounce less violently off the backboard, resulting in a higher chance of the ball going into the net. Finally, we have Phase 5, follow-through. This is when the wrists are still flexed, the ball goes in, and the athlete touches the floor again. Principles that can relate to this is Principle 7, which states that the angular momentum is constant when an individual or object is free in the air. Momentum is a product of mass and velocity. The player as a whole has more momentum than the ball as it has a higher mass, requiring a greater force to change its state of momentum. Momentum can carry the players upwards as they move towards a jump. The basketball has angular momentum as it moves through an arc toward the ring with rotation. Also, the arms and legs possess angular momentum as they move through an angle of movement.
Our expert is Mirdad on the left and our novice is Milton on the right. The differences between their shooting forms will be further explained by Milton in the next part of our video. But for now, take a look at these two shooters and see if you can tell the difference between these two shots. The angular displacement versus time graph explains that the higher the angle of release is, the more successful the shot will go in. From the graph shown, most of the time Mirdad's angle of release was higher than my angle of release, indicated by the red dots. His angle of release is also quicker, resulting in a faster, more efficient jump shot compared to me, where it took time for me to release the ball. You can also tell that my jump shot start position was too high, as Mirdad's had a nice flow throughout his jump shot. From the angular velocity versus time graph's data, me and Mirdad had different shooting forms, causing these different angular velocities. To observe more in depth, this graph can be split into the 5 phases. Mirdad released the ball at 0.42 seconds as I released the ball at 0.63 seconds. You can tell from Mirdad's results in the graph, his angular velocity while releasing the ball was much higher than mine. From that, you can tell that the expert's arm is longer than mine and that the ball was released higher than mine, causing the higher angular velocity for Mirdad. Around 0.98 seconds and 0.91 seconds, both me and Mirdad create this negative angular velocity because of the flick of our wrists. The increase in angular velocity during 1.33 seconds is caused by the arm coming back down around the stomach area. Thanks for watching. Please give us 100%. Thank you.